So in the last lecture, we have used about 1 hour to discuss what is real number and its following definition. We used the 13 axioms, the positivity axiom, the field axiom, and one completeness axiom to define the boundary of the real numbers. And we have talked about the lower bound, upper bound, and the least upper bound, the greatest lower bound, such definitions. And today, we're moving from real number system to a new concept called sequence. And something following the sequence is series. So this is our goal. But before that, we'll talk about how numbers, like integers, rationals, how they are distributed in the real number line. So first, we'll talk about what is the distribution of integers. So distribution of integers, there's one rule. There's only one rule, is that for all of the C in the set of real numbers, there exists only one Z in the integer, in the set of integers, such that Z belongs to C and C plus 1. So what does this mean? It's like that. So first, we suppose we pick one number, C, right? And C plus 1 is defined if C is defined. And there's only one integer in the set of this one. This is not included, this is included. So and this concept is easy to understand because integer is always in the form of 1, 2, 3, 4, 5. So there's only like if you find a number like 3.1, then from 3.1 to 4.1, right? Plus 1. So there's 4. And you exactly pick one number like 2. And from 2 to 2 plus 1, 3. So 3 is not included because it's open, and 2 is closed. So 2 is included. So this is how this is the like this rule is the summary of how the rule of integers are distributed in the real number set. And also let's focus on another concept is the distribution of rational numbers. So rational numbers might be different from integers because they are far more rational numbers in a certain interval. Like if you consider interval C plus 1, then there will be infinite many rational numbers in it. However, they have the same cardinality. So that might be that is one very interesting concept. But actually, if we consider the density of rational numbers, then the density of rational numbers is larger than the density of integers in the real number line. So this is how rational number distributed is for all like randomly pick arbitrarily two real number A and B, and with A smaller than B. So we consider like in this situation, here's A, here's B, and A is always smaller than B, so it's on the left hand side. Then exists a C such that C is between A and B, and is strictly between C, A and B. So no matter how small the interval between A and B, unless A is strictly smaller than B, we can always find C, which is a rational number. In this case, we say, well, this is also say the rational numbers are dense in R. So this is also called the dense, and we will see it later. Okay. And what we left behind from last lecture is the Archimedean property. So Archimedean property is a very useful tool, and it's a standard of define the arbitrarily small, arbitrarily large. So how we mean it's very, very large or very, very very, very small. And this property has two statements. And if we can prove these two property, then we solve the most important concept of math is how small can a number be and how large a number can be. Okay. So the Archimedean property, first one is like for all of the real number which is positive, we'll give a graph to illustrate it. Like this is 0 and this is some C very, very large. It's positive, so it's very, very large. There's a very large distance, but it's defined. And there exists the n here such that n is larger than C. So no matter how large C is, there exists an n that is larger than C, which is a natural number. So this is how we define it. And also in the different concept, let's say we define some number called epsilon. So why we define epsilon? Epsilon means something very small. So every time in the future, if you see the epsilon, the Greek letter epsilon, it's always mean something very, very small. So in this case, let's say, let's do a different version of this one. Let's say, well, here we say this is 0, this is 1, right? And there may be some epsilon very, very close to 0, but it's positive. Then there always exists 1 over n, and n is belongs to not rational but natural number. So n is in the set of natural number. Okay, so this one says even one number is pretty small, and we can always find a number which is in the form of 1 over n, and n is a natural number that is even smaller than epsilon. So this means like the natural number is infinite. It's can larger than any values, and it's reciprocal, which means like 1 over itself can be very small, very close to 0, no matter it's smaller than any positive number that we can find. This is the Archimedean theory, Archimedean property. Okay, so how can we prove this two facts? So first, we'll see how one works. Okay, so suppose there exists C such that all of the natural numbers is small or equal to C, and this is the contradiction of what statement one says, and we are trying to prove like this will reach a contradiction in the end. So if this way happens, then there's a fact that if this one happens, then the set of real number is bounded above, because remember from the previous lecture, we can find a C such that all of the suppose this is n and this is C, right? All of the elements smaller or equal to it, then this is upper bound. So it's bounded above. So we can always find a B. We can find a B, which denote as the greatest, the least upper bound, like which is equal to sup n. So we can always find a B like that. This is from the last lecture's fact. And because B is the least upper bound of n, B minus 1 over 2 is not an upper bound, because the definition of the least upper bound is that all of the number that is smaller than it, and B minus 1 over 2 is smaller than B, is not an upper bound. And in fact, there exists an element in n such that n1, we define this element as n1 is larger than B minus 1 over 2. If this does not happen, then B minus 1 over 2 is actually a upper bound, which is the contradiction already found. So this must be true. So now we are reaching this point. Then how can we make the contradiction that C cannot be larger than any value? This is because remember from the definition of natural number is an inductive set. So actually if n1 is in n, then n1 plus 1 is also in the set of natural number. So in this case, n1 plus 1 is larger than B minus 1 plus 1. This is adding plus 1 on both sides, right? So this fact is right. And how this one looks like? This one looks like that. And B plus 1 over 2 is larger than B. So which contradicts to the fact that the set of natural number is bounded above, because there exists an element in set n that is larger than the least upper bound we defined before. Thus, we reach a contradiction. So statement 1 is true here. What about the second one? What about the second one? Like for all of the epsilon greater than 0 and it's very small, and there exists n such that 1 over n is smaller than epsilon. So how this one true? Actually, we can use 1 to deduce 2. So how we do that is like we define epsilon to be 1 over C. And we see from 1 that n larger than C. This is always correct. We have already proved from 1. So this is same as 1 over n is smaller than 1 over C. And why this is true is by the concept of reciprocal. So 1 over, if n is larger than C, then 1 over n is smaller than 1 over C. If they are both positive or both negative, and this is always true, right? So in this case, we have proved like 1 over n is smaller than epsilon because epsilon is equal to 1 over c. So 2 is true given 1 is true. So this is our final proof of the Archimedean property. And we'll see it once again. Think about it, and we'll see it many times in the future. And these two properties is very useful in math. Okay, and previously we already talked about the upper bound and lower bound. So we'll talk about what is actually some set is bounded. So a non-empty set S is bounded if and only if it is both bounded below and bounded above. So like if we can find a set, we can always find the upper bound of it, and we can always find the lower bound of it. That which means like for all of the element x, if from the set of big X, this is a big X, there exists the C larger equal to X and B smaller equal to X, and this is bounded because it's both bounded above and bounded below. And also a set is bounded can always have a least upper bound and the greatest lower bound. This is also true from the definition. Okay, and there's another theorem. This theorem is very interesting. It says if non-empty set S is bounded above and S is a set of integers, then S has a maximum. So here we are going to define a new concept called maximum. So remember, a set can look like that, and we know like if S non-empty set S is bounded above, then always have a supranom, right? Has always a supranom. But what is the difference between maximum and the supranom? This is very interesting fact. For example, if a set if a set is like x smaller than 5, then does this set have a supranom? Yes, 5 is supranom because for all of the element that is smaller than 5 is x. It's an element of x. However, it is not upper bound of x, so it's a supranom. But it doesn't have a maximum because we cannot find the exact x that is the largest in the set. However, if say like x is smaller or equal to 5, then this have a maximum, both maximum and the supranom. Supranom and maximum is both equal to 5. So this is the difference between maximum and supranom. We need to talk about. And briefly speaking, supranom is like it's not it's an upper bound, it's a least upper bound, but we cannot say exactly which element is the largest element in that set. But we'll say about, well, it has a maximum, then it means like it is also a least upper bound, and we can always find the maximum in that set. We can always find a specific number equal to that maximum. So that's the difference in a brief way. All right. And now this theorem says if a non-empty set S is bounded above and S is a set of integer, then S has a maximum. So what does this mean? It means like integer set that is bounded above is always have a maximum. So we are going to prove it. And actually we can prove it in a very clever way, because previously we have seen how integer is distributed is for all of the C, right? C and C plus 1. There's only one integer, Z, in it. So we'll use this fact to prove it. So firstly, by the completeness axiom, if S is bounded above, then S have a least upper bound, right? So it defines C equal to the least upper bound of S, the supranom of S. And C minus 1 is not an upper bound, because anything smaller than it is not an upper bound, right? So there exists a M in the set such that M larger than C minus 1 in the same logic as we proved above, right? In the same logic as we proved the Archimedean theorem. So M, we can find an M larger than C plus 1 also in the set of S. So we move the term, we turn this inequality around. So C is smaller than M plus 1. which is this one. Okay, and what this means, like S is in the set of minus infinity to n plus 1, right? Because the upper bound is smaller than some value. We can say this is, for example, this is n plus 1, right? And this is C. So the set of S is here. So it must be in the set of negative infinity and n plus 1. So we reach the condition 1. Okay. And how we continue it? It's like, because for all of the z in the set of integers, there is not we cannot find that k belongs to the set of integers such that k belongs to z plus 1. So why this is true? This is because z has a gap of length 1. This is what we say about if c is already found here, if this is an integer, we already prick here, and c plus 1. There's no integer in the set of here, which has a length 1, right? So this means like z has a gap of length 1. So like there's no integer inside this range, both open set. So there exists not a integer k such that k is in the set of n to n plus 1, right? So, and in the case that m is not, m is an element of z, and n plus 1 is also an element of z. So S must belong to minus infinity to m, and m is the maximum. We can always find m such that, well, m is the maximum of that set. And this is easy to see because we will find if we can define C, and the C is the supranom, and like C minus 1 is here, and we can always find the m in between, then m is the maximum because m plus 1 is too large and m minus 1 is too small. So m is unique, and it's the unique largest element in it. So we can find it and define it as the maximum. Okay, so the last concept regarding the real number is called density. So a set of real numbers S is said to be densing the real number set if for all of the elements A, B, if A is smaller than B, the interval AB contains a member of S. So what does that mean is, like, imagine we are talking about rationals, and this is exactly one property of rationals distribution, right? So no matter how small A and B is, we can always find an element S in the set S. So this is density. So which means like it is actually virtually connected from negative some number to positive some number. And this case is called the density of it. All right. Cool. And the first theorem is rational is dense in R. Okay. So we'll use the Archimedean property too to prove this theorem. So first, imagine like for all of the AB, which is A smaller than B, and this case means B minus A is larger than 0, right? And because this one is a positive number, by Archimedean property 2, we can always find 1 over n, such that n is a natural number, which is smaller than B minus A. And if we define C to be nb minus 1, if we can define C in this way, then by the integers distribution, what will happen is like there exists a m in set Z such that m is in the set of nb minus 1 nb because this one is in the set of real number, and there exists only one integer such in the set of a real number from a real number and a real number minus 1. Or in this case, we can find this inequality, right? And so what happens? We divided this inequality by n. And remember, n is a natural number, so it's a positive number. So divided will not change the direction of the inequality. So b minus 1 over n is smaller or equal to m divided by n smaller than b for all of the b of the real number. And now we can say something very interesting. It's like a is equal to b minus a, right? Because b minus b cancel out and minus minus become positive. So a is equal to this term. And what this term is b minus a is always larger than 1 minus n. So by a negative sign, minus a larger number is always smaller than minus a smaller number. So a is smaller than b minus 1 over n. And this one is here. So we can following writing this inequality here. So it becomes like for all of the AB, which is a smaller than B, and they're pretty close, even they're smaller than O epsilon, and it still we can find A smaller than A smaller than M minus M over N smaller than B, right? So reach this point. And what we can say about this point is that what can I say about this? Remember, m is a integer, and n is a natural number, so it's always also an integer. So a division of two integers is always a rational number, right? So this means like for all of the a, b, which is a real number, and a smaller than b, we can always find a rational number in the interval of a, b. So we're done with this one. And another corollary of this theorem is the set of irrational numbers is also dense in R. And actually, irrational number is far more dense than the rational number. But actually, we can say they are all dense now, but we cannot have a comparison between them. So an easy way to prove is using the fact that rational are dense. So because we already talked about before, like the root square of 2 is an irrational number, then there exist positive irrationals because root square of 2 is always positive. So for all interval AB with A smaller than B, we can always choose a positive irrational Y, right? And we can always choose this one. And by the fact that Q is dense, then for all Q in the set of rationals, A divided by Y is smaller than Q smaller than B minus B divided by Y. And the Y is a rational. Because you can say if this is smaller than this one, and this one is also in R, and this one is also in R, right? And even if there are, we can always find a Q between them because we can always find a Q between any two number of real numbers. So if we times Y to the term here, then A smaller than QY smaller than B. And because the product of two rationals are also rationals, the product of one rational with irrational is irrational. So Q times Y is irrational. And yeah, so this is in the logic that that QY is not rational because rationals have the field active. Rationals are closed under the how to say rationals are closed under the multiplication, and the Q is rational, Q is rational, and Y is irrational, right? So their multiplication, their product must be irrational. So I prove like between any two real number A and B, and we can always find the irrational number between them. So irrational number is also dense in R. And that's it is what we left from the last lecture. So today we'll talk about some very interesting thing and some very basic fact about sequences. So we'll first introduce some topic regarding absolute value and how to say some like triangle inequality and some other useful identities to compare the size of something. And yeah, we'll talk about them one by one. So first, absolute value. For all of the real number, its absolute value is denoted by this term, and this must be very familiar with us. And it's defined if x is larger or equal to 0, and is equal to itself. But if it's smaller than 0, then it's the negative of itself, right? So this is the absolute value. Then for all of the x, y belongs to the real number set, the absolute value of x is smaller or equal to y. This one, if and only if negative y is smaller or equal to x, smaller or equal to y. And this is what we define here. Okay. And the corollary is like a corollary of this statement. It's because a real number is smaller or equal to itself, right? So we denote this one by the absolute value of x, this one as y, and we can find out, yeah, we just pick the negative of it, and we can find out this fact. So this fact is like the x is smaller or equal to the negation of its absolute value, smaller or equal to the absolute value itself. Actually, x can only be two values, either this one or that one, and it's in between. It's in between them. Okay, and considering a pair of real number a and b, when we want to estimate the size of a plus b, we could use the following axiom. Usually, like we know what a is, what b is, but how what's the absolute value of their sum? This can sometimes cause a question to us. So the triangle inequality is used to solve this problem. So for all of the element a, b in the set of real number, and the absolute value of a plus b is smaller or equal to the absolute value of a plus the absolute value of b. So we'll give it a brief proof. So by the above corollary, which is this corollary, right? So for all of the AB, real number AB, negation of the negative of the absolute value of A, this one is true from it. And we can also reach this term. And adding these two together, we can find this one. Just add this term to this term, this term to this term, this term to this term, and it will not affect the direction and the property of the inequalities. So we reach this one. And we then we use the we use the distribution property. Then we can find this term. We can write this term in this way, and the last two terms remains the same. And then we can find out this is actually in this form, right? This is actually in this form. Okay. So what's next? If this is in this form, I will find the absolute value of a plus the absolute of b is y. Is y here, and a plus b is x. Then we can find this one is smaller or equal to this one. So the absolute values definition have defined this one. So we have done the proof. Okay, and there's some lemma of it. The lemma, the lemma is very intuitive. It's like the x minus a. If x minus a's absolute value is smaller than r, which is a positive number, then this is same to say a minus r smaller than x smaller than a plus r. And also it means x is belong to the interval a minus r, a plus r. And these three statements are all equal to each other. So this is, we want to say it has equivalent relation between these three statements. And it's very easy to see because between 1 and 2, well, we just use the definition of absolute value. So minus r smaller than x minus a smaller than r, and this is used the fact here. This is used the fact here, right? Yeah, and what we can find out here is we just plus a for the three inequalities, and becomes a minus r smaller than x smaller than a plus r. So 1 and 2 are actually if and only if, so they are equal. They have an equivalent relation. So 1 equivalent to 2. And the 2 and 3 is equivalent because this is just from the intervals definition. Interval defined as this one, right? So 2 and 3 are also equivalent. And because equivalent is transitive, then if 1, 2, 2, 3, then 1, 2, 3 are all equivalent from this fact. Okay. And the second thing is power, right? We began to talk about some algebraic identity for size estimation right now. So first definition, power. So what is power? We have defined 4 operations before, which is sum, product, difference, and quotient. And now the power is different version. So for all of the natural number n and real number a, we can write a to the power of n. So this is the power n of number a. Usually we say the a to the power of n. It means like a multiplied by itself n times. So a to the power of n is actually means this term. So 2 to the power of 5 is equal to 2 times 2 times 2 times 2 times 2, which is, well, 32, right? So this is the power. I think, yeah, it's from elementary school. So traditionally, 2 to the power of 2 we can write as a squared, and this we read a cube or cubic power of a. Okay. And the first identity, algebraic identity for size estimation is the difference of powers formula. So difference power formula is written as the simplest form is a to the power of 2 minus b to the power of 2 is equal to a minus b times a plus b. And it can be more complex. Like, what about the cubic form? Like cubic a minus cubic or minus b cube is equal to 1 minus b times this form. And if we extend 2, 3, 4, 5 to the power of n, then it becomes a minus b times this form, right? So actually, 3 minus 1 is 2. And 3 minus 2, a times 3 minus 2 times b to the power of 3 minus 2 plus b to the power of 3 minus 1. So this is satisfied with this. This one is satisfied with this rule. And this one is also satisfied because it's like it's equal to a to the power of 2 minus 1, which is 1, plus ab, well, b to the power of n minus 1, and a to the power of n minus 2, which is 2 minus 2, which is 0. So it's 1. 1 times b to the power of 1, which is b. Okay. So how do we think about it? We think about it in a very common way. So first, what this term actually represent is we times a inside, and then minus we time a b inside. So this, if we time a here, it becomes a to the power of n plus a to the power of n minus 1b, a to the power of n minus 2, b to the power of 2, plus and last we just time a besides it. And then we plus we minus term of b times into it. And this is the fact that we use the distribution property many times. And this becomes a to the power of n minus 1b, a to the power of n minus 2, b to the power of 2, and all add together. And last term will be b to the power of n minus 1 plus 1, which is b to the power of n. And all those terms here are canceled out. This one canceled, this one canceled, this one canceled, this one canceled. And only remaining term is a to the power of n minus b to the power of n. So we're done. Okay. And the difference of powers formula is very useful in most of the computational method. And it can lead to another identity, which is called a geometric sum formula. So what we do is here, what we do is we take a equal to 1 and b equal to r, and it's not equal to 1. So in this case, we replace n to n plus 1 and divide both sides by 1 minus r. So what will happen is like it becomes we replace a with 1 and b with r and n with n plus 1, right? N plus 1. Yeah, this is what we do, and r is not equal to 1. Remember, that is very important. And this one will be equal to 1 minus r times 1 to the power of n minus 1, which is 1, plus, okay, and this r plus r to the power of 2 plus r to the power of n plus 1 minus 2, which is n minus 1, plus r to the power of n minus 1 plus 1, which is n. Because a is just 1 times something here. So, and in this case, we can divide this term by 1 minus r, and 1 minus r. R is not equal to 1 is very important, because if r is equal to 1, then this term is 0. So it cannot be divided through. So 1 minus r is 1 to the power of n plus 1 divided by 1 minus r is equal to 1 plus r to the power 2 plus something to r to the power of n. And this is exactly what we find the geometric sum formula here. Okay, so we have defined two identities here. And the third algebraic identity is the binomial formula. So binomial formula is very useful in one specific model called binomial model of discrete probability. And this is the most important case that I found. So if you study probability later, you will meet with this formula very, very frequently. And also, besides binomial, you will also meet geometric distribution and a negative binomial distribution, which you will all use the binomial formula. So this is said like for all of the a, b are real numbers, n is a natural number, then a plus b to the power of n is equal to this form. Well, you may not understand what this means. This is just mean n to the power of nk by a bracket, by a very long bracket. It just means like n factorial divided by k factorial times n minus k factorial. And remember, k factorial is 1 times 2 times 3 times 2k. And yeah, and binomial. And this is the binomial formula. So for example, if you want to write 1 plus 2 to the power 4 is equal to what? So first we do 4, 0. Like this 1 to the power 4, right? And plus 4, 1. 1 to the power of 3 times b, which is 2 to the power 1, plus 4, 2. 1 to the power 2 times 2 power 2, plus 4, 3. Yeah, 1 to the power 3, 2, no, 1 to the power 1, but 1 to the power 3 is equal to 1, so it doesn't matter. 3 plus 4, 4, but it's better to write it correctly. Okay, so this is 1, 4, 4, and it's 2 to the power 4. And we can calculate this out. For example, we can calculate 4, 0. What this term means is like 4 factorial divided by 0 factorial, 4 minus 0, which is also 4 factorial, and this is equal to 1. And this is always equal to 1. So if you see something like 4, 0, 4, 4, they're equal, 4, 1 is equal to 4, 3. Yeah, this is the fact by the like the combination, combinatorics of mathematics. Okay. Yeah, this term is always read as chosen A from n items. And we have already seen the summation notation before. And if we use the summation notation, all of these three formula can be abbreviated in these three forms. Okay. Now we're talking about sequence. A sequence. So a sequence, what we usually want to define something look like 0, 1, maybe 2, maybe 4, maybe 10, maybe 100, something like that, and going through. And this is a sequence. And sequence has two properties. First, it is a function. It is a real valued function whose domain is a set of natural numbers 1, 2, 3, 4, 5, 6. and it goes on. And we just calculated by a function that 1 goes to 0, 2 goes to 1, 3 goes to 2, 4 goes to 4, 5 goes to 10, 6 goes to 100. It's just a function between them. Okay. And the function can be explicit, it can be implicit, and it can be irregular, but it is just a function that we can found. Okay, and even though it is a function from natural numbers to real numbers, but we don't write it as a function form. Like we don't write the sequence here, like f is from n to r. Instead, we write every term of fn as an. So what we usually write is an. And we define an as each fn. It's actually something like from take 1 to go 2, this is an, and it's inside a giant bracket. We usually write in that way. Okay, and here n is means the index of the sequence, because usually a1, we say a1 is the first term, a2 is the second term, so n is the index, and an is called the nth term of sequence. So this is the first term, second term, the third term, the fourth term of the sequence. And the sequence can be infinite, so they can be a infinite to means it's the infinite term of the sequence, or we say it goes infinitely, so we cannot find the last term. It's both okay in this case. All right, and what we left behind. What we left behind is some, yeah, we can see some examples of the sequence. So first we say 1 over n is a denote sequence that each term is equal to 1 over n. Yeah, very obviously. Here, 1 over n is the an. This is an, which is a function of taken n to be 1 over n, right? So we can always think of is a function that taken the natural number to go to a real number 1 over n. N is a natural number, and this is an, which is a term here. So we written as 1 over n. And this is exactly the bracket of an can be plugged in. So explicitly we can find out 1 over n sequence is equal to 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and goes to infinite. And this is the first sequence that we define. And second sequence might be a little bit interesting because yeah, it is also an infinite sequence. It has infinite terms. But here, the sequence is defined by this function. So this function has a property. When n is a odd number, then 1 plus negative n is going to be 1 plus negative 1 if it's odd, and negative 1 is still negative 1, and this can be 0. And with even, and this can be 2. Well, in this case, we can define the sequence. We can write it explicitly as 0, 2, 0, 2, 0, 2, 0, 2, because remember, for every sequence, it starts with 1. So it doesn't start with 0. If it starts with 0, then the first term will be 2, but it starts with 1, so the first one will be 0. And 2, 0, 2, 0, 2, and 0, 2, and it continues to be that. Okay, and we have use 2 examples to show what actually a sequence means and what's the relation between a sequence and a well-defined function. And now we can find some other way to write a sequence. So here, sequence can be written in a very explicit form, like some function value in a large bracket. But sometimes sequence cannot usually written in that explicit way. It can only be written in some implicit way or recursive way. So here we'll see more examples of it. So firstly, for function for the sequence an, okay, it's still called an, but an now defined as the largest natural number that's less than or equal to cubic root cubic of n. Then find the first 5 terms of an. So here, an is belongs to the natural number because it's always a natural number. So we can always say a is in the set of natural number and is bounded above by this one. So there exists only one largest natural number by the completeness axiom, and also based on the fact that the the set of integer or the set of natural number that is bounded above always have a maximum. So AN is well defined. You can always find actually one specific term, a specific number for each term. And AN is equal to 1, 1, 1, 1. The first 5 term is 1 because root square 3, root cube n 1 is equal to 1. And 8 is equal to 2. So every term between 1 and 8, like 1, 2, 3, 4, 5, 7 are all 1. And from 8 it becomes 2. And going to 3 start with the 27th, and 4 start with the 64th term. Okay, and this is trend what we found. Okay, and a very interesting thing is like we can also define sequence in a recursive way, which means like we can define A1, and each A1 is based on the fact that AN is null. So this mean recursive way is very similar to mathematical induction. It's like we first define the first term, and if for all of the term that we know like a specific AN, we can always define AN plus 1, and we can define the whole sequence, right? So let's see example. So first define A1 is equal to 1, and AN plus 1 is equal to AN plus 1 over n. If AN squared is smaller or equal to 2, and AN minus 1 over n, if AN squared is larger than 2, then the whole sequence is defined. Why is defined? So first we say A1 can be found, and AN plus 1 is always based on the value of AN, right? So it's defined. Okay, let's check it. So the first term is A1 is equal to 1, have fun. And what about A2? A2 is A1 plus 1 over 1, because A1 square here, A1 square is smaller or equal to 2. It's actually smaller than 2. So A2 is 2. However, when we plug into A2 equal to 2, then 2 squared is 4, right? 2 to the power 2 is 4. And 4 is larger than 2. So A3 is equal to A2 minus 1 over 2. We use this term, and we calculate 3 over 2. And A3 squared is also greater than 2 again. So we use this form again. So we get A4 is equal to A3, which is 2 under 3 minus 1 over 3. And this is actually 9 over 6 minus 2 over 6, which is 7 over 6. And we continue this trend. A4 square is, well, it's this one, but it's smaller than 36 under 72, which is actually 2. So we use the first term again. So A5 is A4 plus 1 over 4. We calculate this one. We calculate this one as our next value. Okay. And yeah. And now we can find this one defined by the recursive form can also define a sequence. So now we find 3 ways to define sequence: explicit way, implicit way, and a recursive way. Okay. And we can see one another example. So first we see the example of AN. AN is equal to 1, 1 over 2, 2 over 2, 1 over 3, 2 over 3, 3 over 3, 1 over 4, 2 over 4, 3 over 4, 4 over 4, 1 over 5, 2 over 5, and this continue. And the question is, can we find an explicit formula for this sequence? So this is how this term is defined. This is defined in a maybe I'll say in a trend way. It is neither implicit nor explicit nor recursive, because there's some terms we don't know, but we just follow this trend to think about it will have some form. So we'll find a rigorous explicit formula for this one. So how we define that? So first we'll first define n, because n is a natural number, and we define n as k times k plus 1 divided by 2 plus I. And I is between 1 and k plus 1. So here, what does this mean? It's like we'll divide AN into some blocks. Like we'll divide AN into something like there's only one number, and there's 2 number, and there's 3 numbers, 3 or 1, 2 over 3, 3 over 3, and 4 numbers, and so on. We want to divide it in this way. And in this case, the I is actually how many element here, and the K is the total number of element inside it. So K times K plus 1 divided by 2 is the length of each partition, and plus I is the index of the element inside it. Okay. Actually, we can think about like, this one is 1, right? This is 2, this is 3. So what we begin is at 4 is like the first element I equal to 1, right? I equal to 1, and here we have what we have is we'll say is 2 over 3 times 4, right? And this one is equal to 6, and there will be 1, 2, 3, 4, 5, 6 term. So it's actually 1 plus 2 plus 3. So 1 plus 2 plus 2k is equal to 2 over k times k plus 1. So this is what we define here. And if we are like clever enough to define n, then we can also define the I. And now an can be explicitly defined as an is equal to k over j plus 1, or like maybe you can write I over k plus 1. It's always k plus 1 because in the previous example, if k over 3, then I equal to 1, then 4 over 1 is equal to how we say, it's the 1 over 4. The value of 1 over 4 is the term of n, and n is 3 times 3 plus 1 divided by 2 plus 1, right? It's actually the 7th term. I will check whether it's the 7th term. It's 1, 2, 3, 4, 5, 6, 7. Yeah, so we are correct. We are correct by this trend. Okay, so we can see another example of the sequence. So now we define a sequence based on another sequence. We define a sequence Sn, and by the geometric sum formula, we can define Sn as r to the power of k. This is and we add the r to the power of k from 1 to n. So this is a summation of another sequence, which is r to the power of k, right? This is a function, r to the power of k is a function of r, and r, yeah, and r to the power of k is a function of r and also a function of k, and k here is a set of natural numbers. So this is a sequence. The domain is a set of natural number. Okay, and Sn is a summation of this sequence, which is also another sequence. Okay, so what is Sn? Sn is r minus r n plus 1 divided by 1 minus r based on the geometric formula. So maybe you will ask, like, I remember the geometric formula is in this form. It's in this form. But carefully, you can remember like the geometric sum formula is defined from k to n, but this is 1 to n. So we will minus r to the power of 0 case, which is 1. We will minus this one by 1, which is this one minus 1, and which is maybe I'll write one more step for you to understand it. So it will 1 minus r to the power of n plus 1 minus 1 minus r, right? So minus 1 plus r, and 1 minus 1 cancel out, and this will be our answer here. Okay, and also Sn, this is when r is not equal to 1, but we cannot neglect the case that r is actually equal to 1, because when r is equal to 1, we cannot use the geometric sum formula. But when r is equal to 1, it will be pretty easy, because every term is 1 to the power of k, which is always 1. So it just means how many terms there are, and there are n terms. So when r is equal to 1, then Sn, the nth term of Sn is equal to n. And that's our answer. And just as this example illustrate, this example give us one idea, a new idea of sequence, which is called series. So series is defined just like the above example. So a series is a given a sequence an. A series can be defined by a formula like Sn is equal to the summation for all the term of an. So why we always say an sequence as n series is because like S is the first letter of series, but S is also first letter of sequence, so that maybe it must be, I would say it might be traditionally like mathematicians call it way, but it doesn't have any specific logic. So series typically potentially means the summation of the sequence term until index n. Yeah, which is also, yeah, series is definitely a sequence, but can a sequence always be a series? This might be a very interesting topic for you to see. Like for all of the sequence, we can always find another sequence that this sequence, our current sequence, is a series of that sequence. If we can prove that fact, well, it will be very interesting. But I have never tried to do that. It's just what the idea I come up with just now. Okay, and for all of the series, there's one specific series that we want to see. It's called infinite series. And just as this example illustrate, the yeah, the geometric sum formula one, this example is actually a infinite series because it never ends. N can be very large. It can continue to, because for all n of the natural number, and natural number is infinite. So that is an infinite series. So infinite series is when the domain of a sequence has cardinality infinite, likely the whole set of natural number. And that is the only case because if it's a subset of n, then it cannot have the cardinality of infinity. So if the domain of a sequence is n, the sequence built up on it is called, the series built up on it is called infinite series. And for every infinite series, there's a fact called partial sum. So for an infinite series, the nth term Sn is called the nth partial sum of the series, meaning the sum of the terms of the original sequence from A1 to A. And this fact is interesting. It's defined in this way. Like when we consider a series, like maybe series, we don't use A, we use S. S1, S2, S3, S4, S5, S6, and it goes to infinite, right? This is an infinite series. We define it as Sn. So this infinite series. So what's the partial sum? So maybe if we only know the first five, maybe we just know the first six term, we already know what's the trend of going on. So maybe we don't need to analyze the series for so many terms. We just need to analyze the first six terms and we can have already good enough estimation. For example, this is the Sn is built on the sequence like 1, 10 over 1, 100 over 1, 1000 over 1, and so on, right? And this is summation of this is 1, this is 1 plus 1 over 10, this is 1 plus 1 over 10 plus 1 over 100. So this decreases very quickly and it somehow like means it converges to some values. So the partial sum here means, well, we can always find the first six terms from k equal to 1 to 6 of the an. We just need to know this, and this is to S6. If we know S6, we know very well how the sequence and the series will behave. So sometimes we just need a partial sum of it, not need to consider the whole infinite series. Okay, and maybe that's the end of today. And we can see one example. Well, this example is like the infinite series. This is infinite series example, and it's based on the sequence 1 over 2 to the power of n minus 1, and this just sum it up for all of the for all of the natural numbers. So it's an infinite series. So alternatively, it can be written as this form too, because it starts with one. Look at that. This is very trivial and very careful fact when we considering sequences and series. This is from n equal to 1. This is from n equal to 0. This is from n equal to 5. And we change the value of n can lead to a big change of 1 over something. So here n is equal to 1, and this is 1 over 2 to the power n minus 1. So what about n equal to 0? So in this case, the first term is 1 minus 1, which is 0. So n equal to 0, first term is 0. The second term, 2 minus 1 is 1. And the second term here is 1 and is 1, right? So we have finished this one. So what about 5? If it's n start with 5, we always want the first term to be 0. It's 1 minus 1, 0, 0. And well, 5 minus 5 equals 0. So this will be the power of n minus 5 as a result. So this is the change of variables or change of the index in the series and also in the sequences. Usually it's very convenient or easy to start with n equal to 1, right? But in some specific cases, maybe start with 5, maybe start with -3 is more convenient, especially when we are doing the complex analysis, we are doing the Lorentz series expansions, we are very frequent or very likely to see something happen with n equal to -4 or n equal to -3. Some negative numbers start even to make it more convenient for computation. Okay, and the next example is an example of finite series. So the sequence is finite. It's 1, 2, 3, 4, 5, 6. Is for all of the n of the 6 number n can be chosen from is the sequence of 1 over 2 to the power of n minus 1. So this is the sequence domain's cardinality is 6, not infinity. As a result, we can say this is finite series. Right. And last thing I want to bring about is previously we already see some interesting fact. Like here, like in the case of the partial sum, we discussed the sequence of 1, 1 over 10, 1 over 100, 1 over 1000, 1 over 10,000, and continues. And such series and sequences have interesting property. That is, as n gets larger and r larger, an or Sn might approach to a fixed real number L. Or for very large n values, the difference between Sn or L, the fixed real number, or we can say L represent the limit, is arbitrarily small. So in the case we can write a graph, like this one is the value of an, this one is n. So as n become very large, an is actually approaching a certain asymptote, approaching a line. And this will be very close when it gets larger and larger. And or maybe this is not an, maybe this is Sn, and because Sn is always increased, well, it might also be decreased because an can also be decreased. The term in the sequence can also be decreasing, can also be negative. So it can also follow its trend. And this property we say is convergency, which is a base stone for developing limit. This is L here, the limit and the calculus world. So the calculus study is based on the fact of sequence converging and series converging. And the negation form of convergence is divergence. So this is a convergent example, but sometimes Sn can be in this form. So the asymptote is vertical. It can always, you don't know, or if it's in this form, it's oscillation between some values. So these two cases are not convergent, it's divergent. Right. So yeah, we'll see the definition of divergence and convergence in the next lecture. So that's the lecture today. And I'll give you a brief view about what we talked about before. Here, 0, 2, 0, 2, 0, 2. This is divergent because it's oscillation. And this one is also can we say it's convergent? It's very interesting. 1/n is actually convergent because it convergent to zero. It's increasing to zero. We know the infinite term can only be zero. So it's also convergent. It's also convergent in this case. Yeah. So that's about it.